Welcome to our seminar, Selecting the Proper Solar System for Your Boat. Depending on the medium you're using to view this presentation, the slides may go automatically forward, or you may be able to manually move them forward or backward using the arrow keys. My name is Tom Trimmer. I'm the founder of Custom Marine Products. We're a company that specializes in solar systems for boats. I am a cruising sailor, have been for over 30 years. And so we all know, cruising sailors, that having sufficient power on board is important to the quality of our cruising experience. In this presentation, we're going to go through an introduction to solar panels. We're going to look at solar controllers, and we're going to look at an overall balanced solar system, as we see here in the diagram. And we're going to design a solar system using our boat as a case study. And then we're going to talk about selecting the proper solar equipment and some installation ideas. So let's get started. The components of a PV solar system, PV standing for photovoltaic, are the solar panel itself, the solar controller that manages battery charging, the battery bank itself, and then the appliances on board and equipment on board that draw from the solar system. A few things to know about PV solar panels. As you're out there researching, you're going to come across terms like monocrystalline, polycrystalline, grades A, B, C. What does that mean? The different types of solar panels: rigid, semi-rigid, semi-flexible, commercial panels versus marine panels. We're going to explore all these different terms and begin to understand the difference and options in selecting solar panels. First of all, there are monocrystalline and polycrystalline solar panels. The monocrystalline tends to be a higher efficiency solar cell. Now, efficiency is measured as the amount of irradiance or light energy that is exposed to the cell that is converted to electrical energy. So it's the percentage of energy converted. Now we're looking at some pictures of cells. The first one here is a sun power cell. The second one is a typical monocrystalline cell. Both of these are monocrystalline, but many of your monocrystalline cells have the wires collecting the electrical energy on the face of the cell. Sun Power has developed a technology to put those wires on the back of the cell, so you have more cell area exposed to the sun and thus a slightly higher output. These tend to be a little more expensive than polycrystalline. At $3 to $8 a watt is really the way they're priced. Polycrystalline are, as shown here in the diagram, are cells that are less efficient. That is, they convert less energy. They're also less expensive. They do tend to be less sensitive to clouds and shading in some cases. The reason for the difference is that the silicon cells are grown like a hot dog. They look like a large hot dog or sausage, and then that is sliced to create the cells. If that sausage is a single crystal, it goes into a monocrystalline cell. If it's multiple crystals, it goes into a polycrystalline cell. Another type that you may run across are thin film panels, but thin film is only 7 to 12% efficient. So we really don't consider those for our marine applications. Now let's talk about grade A, B, or C cells, different quality cells. As cells are manufactured, depending on how the crystal is formed, they will have different performance qualities. And they're graded under a standard artificial light and then sorted by power output. So the distribution of performance is a bell curve, with most of the cells being a B grade cell, which here shows that there are more in this category. What we're interested in for our marine applications, or RV applications for that matter, is the higher output cells in the A category. And even better is if we can get an A plus quality cell, we're that much better off. Because we want the maximum output per square inch on our boat, because we don't have a lot of real estate like a residential installation or a solar farm. Now, why is the quality of the solar cells so important? Well, it's all about watt hours. Watt hours are the number of watts produced in a day's period of time. So your higher performance solar cells are going to produce more power at suboptimal sun angles where the performance would be lower. So as we show in the diagram, in a morning and evening, our sun is not directly overhead, and so we won't get the full output. But the higher the quality of cell, the higher output we're going to get at these less than optimal sun angles. So if we looked at 200-watt solar panels and we average, say, 5 hours of sun a day, a typical lower performance solar panel might produce 500 watts in a day, whereas the higher performance panel will actually produce maybe 650 or even more watt hours per day. So that computes out to about 12.5 amp hours more power in a day from a high quality cell versus a lower quality cell. Now there are several different types of solar panels that have different applications depending on how we're going to use them on our boat. First, there are the rigid panels, which have typically an aluminum frame and a glass covering on them. These panels will give you the longest life. They're certainly excellent for a pole or arch, frame, or davit mounting. And they will give over 18 years of performance. The semi-rigid panels are really new on the market with a lifespan of over 10 years if properly cared for. These are excellent to mount directly to a cabin top or any sort of a rigid surface. And the beauty of these panels is they're low profile and they can be walked on. They have a non-slip finish, a non-skid finish, so that they can be walked on without any concern of sliding around. The third type are the semi-flexible, or often called flexible solar panels. Their lifespan is 7 years or more typically. For the quality panel, an inexpensive semi-flexible panel may only last a couple of years. These are very lightweight. They're excellent for canvas bimini mounting, or can be used on a rigid surface mounting. We don't recommend walking or stepping on these. And some of these, depending on the design, can be sensitive to shading. So all of our panels with the CM Power label brand use the premium SunPower cells. So all of them have a comparable performance because they all use about the same cells. So depending on what fits best for your boat, rigid, semi-rigid, or flexible, you'll get about the same output per square inch. Now, how is a marine panel different than a commercially available panel? Well, one of the areas is the junction box, and the junction box is typically the first point of failure of a solar panel as salt air penetrates into the junction box and begins to degrade the components through corrosion. The rigid panel, marine panel, will have a junction box filled with an inert silicone. So those electrical components have no exposure to corrosive environment. They're typically stronger frames on marine panels and excellent sealants that will handle the vibration and torquing of a boat. They have typically a higher output performance because they're using grade A+ cells, and they're rated at a voltage that is really compatible with 12 and 24 volt battery systems. And many of these panels are wired to accommodate shading. Whereas a commercial solar panel, the junction box is not filled with inert material, so you can have corrosion of the components, which are typically diodes. If they're one of the more premium solar panels, diodes are put in to protect panels and maximize performance when there's shading of some panels and not others. The frames are designed for rack mounting and very stable environment, and their output is typically 30+ volts. And whereas we only need 12 or 24, typically for our marine boats, there's some inefficiency in bringing that voltage down. And there typically are the B grade or B+ grade cells in the commercial panels. So we're going to take a look at solar panel specifications and what to look for on those specifications. I apologize for the busyness of this slide, but if you use this presentation for reference, I think you'll find this handy. First that we look at in specifications is the peak power of the panel. So in this case, we're saying 130 watts in this particular panel as our example. This is the maximum power produced at standard test conditions. Now, standard test conditions is 77 degrees or 25 Celsius with a standard artificial light intensity of 1,000 watts per square meter. So that is the panel output rating at standard test conditions. With very high quality cells, you actually find that the panel will perform above that when it's out in the full spectrum of the sun. Next, we have a voltage and current specifications at a maximum output power or maximum power point. Now, let's just take a look at the curve here, and you'll often see a curve like this on the specifications of a panel. This is a voltage amperage curve, the dotted line, and the red dot is the maximum power point, which is the combination of volts and amps to get the maximum watts. Volts times amps equals watts. If we multiply volts times amps on this diagram, we get this power curve, which shows the power output of the panel under various voltage and amperage conditions. This will vary as there's shading or other things going on in the panel, but what we want to look at and what we want is our maximum power point. Now, the other two voltage amperage specifications are the open circuit voltage, which is this point down here on the graph, and the short circuit amps, which is up here on the graph. These are important when we're evaluating what is the possible maximum amperage and voltage when we're selecting our solar controllers. Another item in the specification that we've already talked a little bit about is the cell efficiency, which is the energy of light energy converted to electrical energy. Another spec is who is the manufacturer of the solar cells. Sun power solar cells are most popular. It's important to note that sun power cells are made in 4 different qualities. So there is a lower quality sun power cell and a premium quality sun power cell. The premium quality cells typically today are about 23.7% efficient. Then we have the overall panel efficiency, which will be less than the cell efficiency, because there are portions of the panel that have space between the cells that are not producing power. Final item is the temperature coefficient. Well, this is typically between 0.3% and up to 0.6 or 0.7%. This is the amount of degradation or reduction in performance based on heat. So we said our panels are rated at 25 degrees centigrade. Well, let's take a look at a panel operating at 55 degrees centigrade with a temperature coefficient of a -3%. So what is the impact of that? Well, if we take 55 minus the 25, we get 30 degrees centigrade above what the panel is rated at. That 30 degrees times our -0.3% gives us a 9% power loss. So as the panel heats up, in this case, heats up to 55 centigrade, the panel will actually reduce in performance by 9%. I thought we'd take a minute here and talk about wiring of solar panels. 2 options, series and parallel. You'll hear both terms. A series wiring is taking the positive of one panel to the negative of the other panel and wiring them as a string, if you will. In our example of 100-watt panels, 18 volts and 5.6 amps, when we wire in series, the solar array, we add the voltage together. So this would be a 36-volt array at a 5.6 amp output. If we wire them in parallel, which means we bring the 2 positive or all of the positive wires together and all the negative wires together, the array then has 18 volts of output voltage, and we add the amperage, or 11.1 amps of power. So in the one case, we increase our amperage, and the other case, we increase our voltage. So we have different power curves depending on which way we go. We typically recommend wiring in parallel whenever possible. This is because we only need 12 or 14 volts for our 12-volt batteries, or we also need a lower, around 26 volts for a 24-volt battery system. So we have a much more efficient system if we wire in parallel. And also, the more premium panels contain diodes in the junction box, as we discussed earlier. And those diodes prevent a panel that is shaded from bringing down the performance of the other panels. The diode is like a one-way switch. So on a boat where we have some shading, parallel wiring is often preferable. So let's move on to solar controllers and what they do. The purpose of a solar controller is several-fold. First, we want to optimize the power output of the solar array. We want to find that maximum power point so we can get the optimum voltage amperage out of our array. The second thing the controller does is to regulate the amount of power going into the battery. So that prevents the battery from overcharging or overheating. And at night, believe it or not, a solar panel will actually absorb power. So the controller prevents the panel from absorbing power at night. So you can look at the solar controller as the negotiator, if you will, between the solar system and the battery system. The solar system has its performance characteristics with an optimum voltage amperage combination. The battery has its own characteristics of what it will absorb in being charged. And that voltage amperage combination, the MPPT controller takes care of that. Let's look at an example. First, there are two kinds of controllers. There is the PWM, or pulse width modulated controller. Now these controllers are typically less expensive than the MPPT, and they modulate the pulse to the battery to control the voltage. They tend to stream full power to the battery bank when the bank is low, and they're very useful if the panel voltage is around an 18 to 24 volt panel. These can be a very effective alternative. The most popular on the market is the MPPT, or maximum power point tracking controller, and it is essential to use on commercial panels where we have over 30 volts, and you'll see why in just a minute. And it optimizes the power of the solar array so that it goes out and looks at the voltage amperage of the panel based on how it's performing, if it's shaded or not shaded, what that power curve looks like, and pulls off the optimum voltage amperage combination. If we have to do that, it takes some power, so that if we have a limited number of watts in our solar array, like 100 watts or even 200 watts, and we're using panels that are rated somewhere around 20 volts, the MPPT is not necessarily as efficient as the pulse width modulator, because they are more expensive and they do draw some power. So for your smaller arrays, the PWM approach is excellent. For your larger arrays, the MPPT. Now we're going to look at an example of how maximum power point tracking works. So in our example here, let's say that we have 200 watts of solar in our solar system, and we're going to want to put as much of that 200 watts into our battery bank. So our watts equals our volts times the amps. So in this system, in this 200 watt solar system, if we have panels that are around 16 to 22 volt panels, they'll typically put out, let's say, 18 volts at 11.1 amps. So this goes back to our earlier example. The MPPT controller will bring that voltage down to 14 volts and raise that amperage to 14.3 amps. So we get a bit of benefit out of MPPT using the lower voltage panels. But for a small array, it's not really all that significant. For a larger array with higher voltage panels, let's say that we have 36 volt panels that would be wired together in our example, producing the 5.6 amps. What the MPPT controller will do is it'll bring down that 36 volts to 14, but it will raise that 5.6 amps up to 14.3. So you can see that the low amperage, low voltage panels, we get some benefit from MPPT, but not all that much. From the higher voltage arrays and the larger arrays, we get a significant improvement in the reduction of voltage and the raising of current. because in charging a battery, our goal is to have the maximum current going into the battery we can. So again, looking at our maximum power point, our controller will search out along this curve the best power point based on the shading or the amount of sun on the panel and select that for feeding the battery. Now, we're often asked, well, can I combine different kinds of panels in my solar array? We don't recommend that. In fact, we suggest that if you're going to have different types of panels, each panel type should be on its own controller. Here's why. If we have two different types of panels, we could have two different power points. Each panel could perform differently. And so that the power curve can be very complex, and the ability to find the maximum power point with different kinds of panels can be very complex and lead to tremendous inefficiency. Whereas if I have each dissimilar panel on its own controller, we'll have two maximum power points and we'll get maximum efficiency. So that's why we recommend keeping a solar the same. Now let's talk about how the solar controller charges a battery. We're going to look at a lead acid battery, and we'll look at a lithium iron phosphate battery and just take a look. The voltage, battery voltage, will be applied in 3 phases by a typical controller. When a lead acid battery is low, the bulk charging phase puts as much current, here this is current, it will put as much current as the battery will take to bring the battery up to its voltage, its rated voltage. So it may be 12.8, typically something like that. So you want maximum power to pour the power into the battery to get it up to voltage. Once that battery is at its voltage, it goes into what's called an absorption phase, where the voltage stays the same, and it still takes as much power, but as the battery charges and nears full charging, the inefficiency of charging increases, and it will accept less and less power. So the power curve kind of looks like this. Then when it is near charge, it will go into a float mode where it drops down to a float voltage and a float amperage. These are the 3 phases of charging of a lead acid battery. Now it's important to note that MPPT is used here in the first stage, this bulk stage, and actually even an MPPT controller will go into a PWM mode here for the absorption phase. If we look at a lithium iron phosphate battery, its charge curve is quite different. It charges, if it's low, we want a bulk charge to get us up to the voltage, and it will continue to take a maximum current all the way up to nearly full charge, within 95 to 98% of charge. It'll take all the current. So we don't have a current reduction, we have a constant current. When it nears that final phase, you can go into a float mode, although not necessary with these, and it then drops off. The controller will drop off to a float mode once the battery is charged. So this is how the controller, and this is a solar controller, it could be your shore power controller, whatever, controls the charge of your battery and prevents overcharge. I just might add that equalization, which reduces the sulfates in the battery and increases performance. Typically, a controller will do that once a month at a very high voltage, maybe 15 volts, to knock the sulfates off of the lead cells. In a lithium iron phosphate, there's no equalization necessary. let's talk about a balanced system for a minute. And we're going to go to and talk about our battery system. Let's first use this analogy of a bucket of water and assume this is a battery bank, if you will. So we have water water coming into the battery, controlled by a valve or a controller, if you will. And we have water coming out of the bucket, being used to water the garden or whatever the case may be. Now, if we compare that, we have the same thing happening here. We have our power feeding in, our controller as the valve into our battery bank, and we have the usage of the power to our panel, through our appliances, instruments, and equipment. If we have a limited capacity bucket, a small bucket, we're not able to store all the power that comes in from our solar, so we have wasted power, if you will. We have no reserve in our bucket for cloudy days. We've got to monitor this bucket of what comes in and goes out very closely all the time. On the other hand, if the bucket is properly sized, we've got plenty of capacity to handle the solar power we're putting into the bucket, and we have plenty of capacity to handle what's coming out. And we typically want a battery system that will, as cruising sailors, last us 24 to 48 hours just off of battery power while we're at anchor. So we don't have to run the generator or the main engine to charge the battery. So the size of the battery is very important. Now let's move on to our case study. We're going to use our boat, my boat, and its solar system and its power generation. So let's take a look. The first thing we want to do is decide, what do we want to achieve from our solar system? Do we want to keep the batteries charged while we're on a mooring? Maybe keep refrigeration running, maybe not. Maybe just keep enough charge so we can keep the bilge pump going if necessary. Or another B would be, we like to anchor out and we want to supplement our current usage so that we can run the engine or the generator less while we're at anchor. Or we might want to generate all the power we need while we're at anchor, C, so we don't have to run the generator or the engine at all to power while we're anchored in that beautiful cove with wonderful peace and quiet. Or another thing we may want is we sail or power a lot and we want to generate all the power we need both at anchor and when we're on passage. So for our purposes today, we're going to select C. We want to generate all the power needed while at anchor. So let's get started on what we. First, there are 4 steps to designing our solar system. The first one, and the most important starting point, is to determine what our daily power consumption is. How many amp hours of power do we consume in a typical day? Once we know our power use, we can determine how much solar power we need to supply the power or keep the bucket full, if you will. Once we have that, we can select our optimum solar panels and controller for our system. Finally, we'll determine the optimum size of our battery bank to be sure that we have sufficient battery capacity for the system we're designing. So these are the steps we're going to go through one at a time. To do that, we're going to use a worksheet, a spreadsheet. Now this spreadsheet is available on our website at custommarineproducts.com. You can download it and use it at your leisure. It looks complicated. It's actually, we're going to go through it a step at a time, and to show you how to. There are 4 sections in the spreadsheet which match to the 4 steps that we just discussed. Step 1, determining our power requirements. Step 2, determining how much solar we need. Step 3, selecting our solar panels and our controller. And step 4, analyzing our battery capacity. So it's all done on this spreadsheet. Let's go through it and give it a shot. The first thing we want to do is determine our consumption for our DC systems. So here we have our amps consumed by each of our appliances. Now these are the amps consumed on our boat, and we find that we're not untypical to most other sailors. We have refrigeration on board that draws about 5 amps. And it's not the newest refrigerator in the world, and it runs for about 10 hours a day. We have other appliances. We have radar. We have LED lights in our cabin. We have our anchor lights on at night. We have our VHF radio. All different kinds of things that we do, including charging our phones. So we determine the number of amps that are used for appliances. When an anchor, and then how many hours are they used in a day's period of time, or a 24-hour period. We multiply those two together and we get our daily amp hour usage at anchor. So in this case, we've got 71.5 amp hours used in a day. Now we're going to use amp hours because our batteries are typically measured in amp hour output. Then we do the same thing for on passage. We take the appliances, the amount of time they're used in a 24-hour time frame when we're under passage. We multiply those together and we see what our amp hour usage is when we're under passage. So that's our DC. The next thing we do is we look at our AC. So if we have an inverter, typically the AC appliances are measured, their consumption is measured in watts. So if we take, like, we have a microwave that draws 1100 watts and we'll run it for 1/10 of an hour a day, the system will compute for you that is using 10.5 amp hours. And so it takes the watts divided by the volts times a factor in inverter inefficiency factor of about 1.2 to come up with our consumption of AC. Now the windlass, which is here, is not used. I put it in here just to remind me to comment that usually when we're using our windlass, the engine is running. So the alternator from the engine is feeding the windlass direct. So that doesn't really impact our draw that much. So then we come up with our amp hours consumed in a day. And these are 2 key numbers that we're going to use throughout the rest of our case study. Let's say that we have a 12-volt system, so we're typically charging the battery at 13 volts. So volts times amps is watts. We multiply the 13 times the 81, and we get our wattage usage consumed in a day's period of time. So this is step 1. Ballpark is good enough for this, but it is key to driving everything else in our analysis. We take our amp hour, again, our amp hours per day times the voltage of our system, and everything in gray, by the way, is what we can change in the model. We get our watt hours per day. Now, we talked a little bit earlier about sun angle, And depending on where you are on the globe, the average hours of sun per day will vary. And you can actually look this up on the internet. You can do some searches and put in your location and come up with the average amp hours per day in your location. We're in the Michigan area. 5 is a good number for our latitude, longitude, and if the panels are mounted flat, 5 is a good number. Now, if my panel is on a pole, actually like it is on our boat, you can tilt it and rotate it, you get about 30% more, so that would be about a 7 average amp hours per day. Significant difference. So that takes into consideration all of the sun angles per day and gives us an average hours per day of full sun. Now then we can put in our battery charge inefficiency factor or efficiency factor. Lead acid would be about 1.2. So there's about 20% inefficiency in charging a lead acid battery, whereas a LiFePO battery, it's 4% or less. So we put that factor in, and that's the watts then that we need to replenish our battery. So from our 81.7 amp hours, we determined our watts. We divide that by 5 and our inefficiency factor, if you will, or our efficiency factor, and we come up with the fact that we need 254 watts of power to replenish our battery bank from the use in a 24-hour period. So now we go to step 3, which let's take a look at the solar panels and the controller. And so, excuse me, if we say we're going to use a 130 watt panel and we're going to put in 3 of them, or we can just put in our wattage, the system will tell us how many panels we're going to need under passage and at anchor. Let's say we're going to use 3 of them. Here the system will tell us how many amps we need in our controller. So the solar controller is measured by its capacity in amps. This gives us a sense of our controller we're going to need. And then it computes how much power we're going to generate from those solar panels, given the 5 hours of sunlight that we specified earlier, average sunlight. We know that we draw down this number of watts, 1,061 watts of power from our prior slide, and we see that that's going to give us an excess. 3 130 watt panels is going to give us an excess of 693 watts a day. So are we over designing? Well, maybe, maybe not. We're going to take a look at that. But under passage, when we use more power, those 3 panels, we're going to end up with a panel deficit, and we're going to have to do something under passage and address that. Now, here's where that excess capacity comes in handy. We want to factor in cloudy days. So on a cloudy day, a solar array may produce only 30% of its rated capacity, or it could be 40 or 50%. It could be down on a heavy, heavy cloud day. It could be down around 20% from the clouds. So if we say, well, okay, we're going to assume we're going to go down to about 30% performance on a cloudy day. We're only going to generate then, instead of 1,750, we're only going to generate 526 watt hours. So I'm going to have to draw from my battery, and to make up that, I'm going to have to draw down that much from my battery. So if I want to, so then we say, well, how many cloudy days do we want this to work for? Say 2 cloudy days. Well, then it tells me that it's going to take a day and a half to come up, bring my batteries back up to speed on sunny days. So that's a pretty good configuration for our at anchor environment. So we literally a day and a half later, we're going to have our power back full and running. If that's not good enough, we can go up here and we can add an additional panel or additional solar, and it will tell us what the impact is. And because we're negative on the under passage, it isn't going to make it up for us. So this is a very nice analysis to play with to determine how much you need under different conditions. Now let's take a look at our battery bank and for our balanced system. This is our fourth step. On a lead acid battery, we only want to draw those down about 50%. We said we're going to do this first scenario on considering cloudy days, and if we have a battery rated at 120 amp hours, our battery bank, and we can only draw 50% down from them, this system then tells us the capacity we need is 164 amp hours to meet 2 cloudy days. And so we'll need at 1.4, or round it up, I guess, to 2 120 amp hour batteries to meet our 2-day requirement. Or we'll need 4.5 batteries to meet our under passage for 2 days and still have capacity to power all of our systems. Another scenario, scenario 2, is what if we have no solar on our boat and we want 2 days reserve capacity from our batteries. They're lead acid, so we can only draw down 50%. And we want to use 120 amp hour batteries. We'll need 3 batteries instead of the 1.5 batteries. So without solar, I need more battery power to meet my 2-day requirement of cloudy days. So this gives us a tremendous amount of information on this worksheet. So here we go through all the numbers from determining our amp hour usage, using that amp hour usage to determine how many watts of solar we need, to determine if we use these 3 of these panels, how many sunny days does it take to make up for cloudy days, and what is my battery capacity with solar. So it really gives us a lot of information about designing our system, and we can play with the numbers and decide what we want to do. Skip that slide. So if we wrap up our findings here, we see that our power consumption was between 82 and 177 amp hours. Our optimum battery capacity is 300 to 700 amp hours if they're lead acid. And our rated panel wattage is we need between 300 and 550 watts of solar, depending on anchor or under passage. So watts times amps equals volts. So this is what we need. So that generates all of our power. So now we have a complete balanced system. We have the right amount of solar. We have an adequate controller. We have a battery bank that meets our needs based on the usage of power that we have on our boat. I wanted to show you just what specifications may look like. These are our CM Power solar panels in the semi-flexible, semi-rigid, and monocrystalline and polycrystalline categories. These are the voltage, amperage items parameters we looked at, our cell efficiency, our cell manufacture, the cell layout. So a 4x8 means that 4 cells across and 8 cells down. And then the panel size, so we can take a look at these various sizes and determine what sizes best fit our boat. And we can take that and move it back into our working worksheet and determine how it's going to work out for us. And then it this tells us how many, at 6 hours of sun, how many amp hours can I project that I'm going to get a day out of the panels. So below is, thank you for attending. Below is some contact information. If you have questions or comments, feel free to call me or any of our folks at Custom Marine Products. Go to our website at custommarineproducts.com. Under support, manuals and info, you can find this presentation, and you can email me at tom@custommarineproducts.com. Thank you very much for attending our presentation, and we look forward to talking with you in the future.